Thank you. How are you guys today? Nice. Okay. Yeah, I'm nice too. That's good. Well, thank you for coming. And what my lecture is going to be, it's going to be in two parts. Okay. So what I'm going to talk about first is what we call the golden ratio. And the reason I'm going to talk about that is because I want to actually talk about this shape right here, the dodecahedron. Okay, it's dodecahedron. It's a 12-sided shape made up of 5 polygons, which are called pentagons. Okay, and what I did is I created what we call a Rubik's Cube type toy that in Canada that actually each side rotates like a Rubik's Cube. So what I'm going to show you guys is how I actually created it. Okay. Now the first part with golden ratio, the reason I'm going to talk about golden ratio is because this shape is absolutely chock full of golden ratios. Now I'm going to hopefully be able to show you that in the second part of the lecture. Okay, so the first part, I'm going to talk to you about the golden ratio and how you see it in society and nature and so on. And then I'm going to get into the actual shape and actually how I created this model. And this model is just a static model, but the one I have in Canada, which I'll show you a picture of, actually turns. I will show you how I created that and the mathematics behind that. Okay? So I made this yesterday out of cardboard from the copy room, and it took about a few hours to make because you have to make it it's very regular, so it takes a long time to actually cut them. But it's a beautiful shape. It's actually one of the platonic solids, which we'll talk about, that the Greeks knew about. Okay, and they used this to represent the universe in their mind. Okay, so this was the most sacred shape in ancient Greece. Okay, all right. So I'm going to move back to my computer here, and let me just talk about the Rubik's Cube. Let's go here. And this is the general Rubik's Cube, and in Chinese we call it Mo-feng, I believe, right? Okay, and it was originally called the Magic Cube. So it became the Rubik's Cube, and if you remember, most of you guys are familiar with the Rubik's Cube. It's a 3-dimensional, 6-faced rotational combination square puzzle, and it came out. The name Rubik's came after the guy named Ernzo Rubik. Okay. And this shape actually won Toy of the Year in 1978, I believe. Okay? And the first thing I did is, with this Rubik's Cube, is I created my own. So here's my own Rubik's Cube. Okay? So this is not the shape I'm going to talk about, but I started with this one first before I got into something more complicated like this. Okay? And this was made out of wood. It's nicely finished, and each side will rotate. Now there's no colors on it. Okay? I didn't put any colors on it. But I just wanted to create each side to move independently. So if you remember, if you're familiar with Rubik's Cube, right, each side will rotate independently. So this can move over here, or here, or here, or here, or this can move around this way. Okay, so basically, this cube came out of a challenge to Mr. Rubik, was that people thought that they couldn't make this type of shape, and the guy challenged him, and he proved them incorrect, that he could indeed make such a shape. Okay, so I basically created this in Canada and made a new one of my own, out of wood actually, and the pieces inside are just the sort of little balls that hook into it. Okay, but so I started with this one, and the knowledge that I learned from this one, I was able to create something deeper. So what I did. Okay, now this is Rubik's Cube is part of a platonic solid. And as you know, in mathematics, there's 5 platonic solids. Okay, so there's a tetrahedron here, a cube. So as you know, Rubik's Cube is a platonic solid. An octahedron, dodecahedron, right? And then finally the icosahedron. The icosahedron is 20 sides to that. So in order to make such a toy, okay, where you have each side independently move, and that this side could be on that side or over here, you have to have a platonic solid type shape. Okay? So I figured that, hey, why not make a dodecahedron? Now I found out later in China, okay, when I was going to the store, I actually saw one of these made. Okay? I didn't know that at the time, but I actually saw, and I couldn't find one unfortunately, I actually saw a shape like this where you can move each side. But I didn't know that in Canada. But anyway, no worries. So that's the platonic solid. So just quickly about a dodecahedron, it's made up of a regular polygon. So regular polygon means, if you guys remember your mathematics, that each side is the same length and the angles are also the same. Okay, so if you notice, maybe it's hard to tell from here, but I will show you this later, but each corner has the same angle, it's 108 degrees. Okay, and each side is the same length. That's what we call a regular polygon. Okay, regular means same lengths, same angles at each corner, okay, each vertex. So in a regular polygon, if you join 20 of them together, then, 12 of them together, then you end up getting that dodecahedron. So that's what I started with, okay? And this is what I created, okay? It's kind of sagging. The reason it's sagging is because it's made of wood, okay? This is I took this picture in Canada. Each side moves, okay? But it kind of sags because it's made of wood. And the pieces, you'll see the pieces connecting into it are a bit loose because I need a proper manufacture to make a ball to sit in the track really tight, okay? But in this case, it's really just a prototype. I was planning to take this and give it to somebody to see if they could manufacture it. So that's the shape. I'll show you that later, okay? So let me just talk to you now about the golden ratio. So as I said, part one, because I want to show you how I built this. So it's a lot of math went into it. But actually the math is not complicated. It's really just maybe middle school math. If you know basic geometry, you can actually create this. Okay, and I'll show you, hopefully, okay? But it's based solely on the golden ratio. So I want to talk to you about what the golden ratio is, just to familiarize you with that. And if you're not sure about the golden ratio, you will, okay? So, continuing with part one, I mean, the golden ratio, many cultures have known about it. The Egyptians, the Greeks, obviously here in China, it's been a long time. It's often called the divine proportion or divine ratio. The word divine means kind of like heavenly, something that's almost spiritually, it's like a really special kind of relationship, or even the golden constant. And it's been explored for centuries, and it's basically this right here. It really means A plus B. So you take a line and you separate it such a way that the sum of the two lengths, okay, is to the longer length, okay, as the longer length is to the smaller length. If that makes sense or not. It's a special ratio, okay? And I'll just describe it here a little more here. And if you create that ratio, A plus B to A is equal to A over B, you get this ratio phi. I'm going to use that word a lot, phi. We call this phi. Some people call it phi, but I like to call it phi. And if you set B equals to 1, and you take the positive answer, you get this wonderful number, 1 plus square root of 5 over 2. And that is the golden ratio. So it's actually an algebraic number, if you guys are mathematicians. Okay, there's two numbers actually in mathematics. Transcendental numbers and algebraic numbers. And this is an algebraic number, okay, which is very unusual, because pi is a transcendental number, e is a transcendental number, and so on and so forth. But in this case, we get solution. Phi is about 1.62. Interestingly, kilometers and miles is almost the golden ratio, right? About 1.62 kilometers is about 1 mile, okay? So that's how you can solve that number, okay? So that's the golden ratio. Now, another one you can look at it, we often don't say that this is the golden ratio, we can even say the golden triangle, the golden rectangle. So again, A plus B to B, okay? So there's many different relationships how you can depict the golden ratio, all right? And here's other ways you can get the golden ratio. So you don't need to worry about it. It's no test at the end, okay? But if you take the continued fractions of 1 plus 1 over 1 plus 1 over plus 1 over 1, you know, so on and so forth, you get the golden ratio. Another one, phi is the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of, you keep going forever, you get the golden ratio. Weird, right? Or you can remember this one. That's a bit complicated. Also, phi is 2 times cos, again, pi, the most important number in mathematics, over 5. So the golden ratio comes up over and over again in mathematics. Okay? Now, how do we see it in nature? Well, here's this in nature or other mathematics. Let me just bring this up. The golden spiral. I'll show you an example of this in nature, but the golden spiral also is a logarithmic scale. And you can see here is phi, and then to 1, right? So 1 to phi, it's golden ratio, right? So golden rectangle, you got 1 to 1 over phi. Interestingly, 1 over phi is also phi minus 1. Very interesting relationship, okay? And then if you quarter it again, 1 over phi squared, 1 over phi cubed, you keep going and going, you get this beautiful logarithmic scale. And if you look at it carefully, it kind of looks like an ear or a shell, right? So that's a very common shape. And I'll show you examples of that. You're often seeing triangles. This is an amazing construction, George Odom's triangle. Again, shows that A to B, A to C to A to B is simply saying A to B to B to C. Okay, it's the same relationship, you get phi. I mean, it's an amazing construction. So it shows up in lots in mathematics. Okay. So here's some examples of nature. Yeah, I don't know, this is Fergie, I think, if I remember right. Okay, a young Fergie, right? But it shows up in the human face a lot. You can see, right, a golden rectangle, just as I showed you. I mean, if you take the ratios between the eyes, okay, ratio between the eyes and down towards the nose, again, 1 to phi. Okay, 1 to phi, phi being the golden ratio. Even this, when you split the nose in half, okay, in this way. Even teeth, good set of teeth, often follow the golden ratio. So I showed you here, the ear, right? I mean, it's not exact. There's obviously variations, right? If you're an elf or Spock, it doesn't fit the golden ratio, okay? But for humans, yes, it fits the golden ratio. And this was also shown how the human body has full of golden ratios in it. And also the same thing with Leonardo da Vinci. He did Vitruvius Man, you know how the guy like this, he showed many golden ratios in the human body alone. Okay? So these are just a few of the examples that you see in everyday life. Just the human body, for example, not even everyday life. Even in the hand, how the bones in your fingers are related. It follows again. The longer one is phi, the shorter one is 1. So if you divide the longer one by the shorter one, you get phi. Doesn't matter the length. You just divide those and you get the same thing. You get phi. Even the heart rate. Fascinating. Butterfly. For some reason, it just shows up over and over again. We're not sure why. And I'll show you briefly, but I won't take a very long time. In the second part, I will show you just briefly how the Fibonacci numbers relate to the golden ratios and what the Fibonacci numbers are. So, I mean, it's just some amazing relationships. Some people think, and I probably agree, that if you really want to find the golden ratio, you can find it everywhere. But it doesn't necessarily mean it's divinely created into the human body. It's just that it seems to pop up in very interesting ways over and over again. Okay. A spiral of a shell, and it's interesting as this shell keeps moving around. Okay, it always follows this. Oops, what happened here? It always follows this golden ratio. Don't know why. Okay. So again, it just shows up in organisms over and over again. It's very common. So it's just an example. And again, you can see it's like a logarithmic scale, right? Just like that previous picture I had. It's amazing. In art, Leonardo da Vinci. And he noticed that if you follow this, what do you got here? Logarithmic scale, right? It goes around and around, right? Actually, sorry, it should go this way, pardon me. This way, right? Like this. So, Whether it's by design or not, I'm pretty sure this is by design. Statue of Athena, again, ratios are put in there. So art and math really sort of joined forces in a way back in the Renaissance, because they felt that these golden ratios were divine, okay, spiritual, that if you incorporated these things, you were sort of praying to God in a sense, okay, so they often put these in. But it turns out that human nature, the human body and other nature tends to favor the golden ratio, and it seems to be more aesthetically pleasing. So that raises another question, which we won't get into. Is the golden ratio naturally aesthetic? Is it something that we just like to see? Is it a good ratio? Is it just something that we feel best with? And they've done tests on it, but it's been mixed results. But we're not really sure if it's something that the human mind likes or what. But some reason it keeps showing up over and over again. And we're not just picking random spots. We're actually choosing chin, the forehead, and things like that. So. Yes?
Has it shown up in other non-Western arts?
Oh, I don't know about that. But I mean, and I'll show you the pyramids next. Definitely showed up there. But most cultures knew about it. Anyone who delved into mathematics knew about it a lot. Again, Dean Leo and I talked about it before. It was Huanjin. What's the last part? Ingenious? In English? Chinese in English? Huanjin. Huh? Beili. Okay, there we go. Okay, not BF, right? I'm joking. Graduation. Okay. In the pyramids, so I'll just quickly mention this. Don't worry about all the math, but it shows up in the pyramids. So the Egyptians obviously, again, did they really know about this? Well, I think it's complicated enough that they had to know something about phi and about pi. Why did they encode it into the buildings? Well, we really don't know, okay? But in this case, we take A and B and the height of the pyramid, okay? So B to H to A, you often see 1 to the square root of phi, which, by the way, is very similar to 4 over pi. Pi is, as you know, is the most famous or the most important number in mathematics, really. To phi, and also you see 3, 4, 5. You all know 3, 4, 5. It's the easiest Pythagorean triple. And the other one you see is 1 square root of 4 and 1.61899. Actually, this is really the same as that. So these come up. We don't know why in the pyramids, because we don't know why they created them like this.
Maybe it's more beautiful.
Well, that's the thing, and that's a great statement, because they're saying, why do people study anything? Is it because of beauty? And what is beauty? How do we define beauty? That's a big question. In fact, in my IDS class, that's a big portion. Actually, that's one film. It's a big portion of the film. They talk about what does it mean to have beauty. It's called Beautiful Equations. What does it mean to define beauty? And that's a difficult question. And that's really where mathematics and art, or science and art and religion kind of all come together, because that's what we're trying to find. We don't really know. Okay? Again, just some quick examples of some architecture. Again, sorry, this way, pardon me. Right? Golden spiral. Greeks used it heavily in their art and in their buildings. And there are things Greeks did too. You notice that the buildings were never built straight, right? They're always built at an angle, so when you looked up like this, you didn't feel like the building was going to fall on you, right? It looked more naturally straight. Even though it's not straight, it's tilted inwards a little bit. Again, no one really knows. Is it done by design or by aesthetics? No one really knows, okay? Closer to home, CN Tower. Everyone know CN Tower?
No.
Right? Dual in dual? CN Tower in Toronto. Okay. So this was built in 1974, I think, 76, 74, something like that. And again, if you look at the top, if this is 1 and this is phi, okay, you just take this one divided by that one, you get the golden ratio, about the golden ratio. it's aesthetically pleasing. I mean, if you think about it, right, with the CN Tower, I mean, imagine this dome was down here or up here. It wouldn't kind of look right? It kind of looks good, doesn't it? I mean, it's not a science. This is nothing scientific. It just kind of, yeah, it kind of looks good. That you got the observation tower right about here. Whether it's by design or not, we don't know. Have to ask the designers. Okay, India. Well, of course, Notre Dame is no real order here, but Notre Dame filled with golden ratios. In Paris, okay, I've seen it personally. It's a beautiful cathedral. I've been to Taj Mahal twice, and it's just absolutely littered with golden ratios. And the first time I went, I was in awe. The second time, I was even more in awe. I don't know why. I felt more, I don't know what the word is, more awestruck the second time I went. It's just literally so pleasing. You just sit there and it's like, oh, it's nice. Okay? Don't know why. Maybe it's the golden ratios. We don't really know, but it's a beautiful, and you can see it's completely covered. It was built by the Persians in 17th century, and it's just absolutely littered with golden ratios. Okay? So that's some architecture. Okay, so now what I'm going to do is, now I've described the golden ratio, what I'm going to talk about now is go back to my shape, and I'm going to go through some mathematics about the shape and what I had to do to build this thing right here. Okay? I wish I could have found a model. I went looking everywhere for it, one that could turn, you know, but I couldn't find one. So anyway, I can pass this around. You guys can play with it. Okay, it's nice. It's manipulative, right? Gets you to play with. I made it yesterday, like I said. Yeah, you can play with it. It's like a soccer ball. You know, you kick it, right? Okay. So I'm going to pull this out, and I'm going to go pull up Mathematica here. Oh. Oh no! What are you guys doing? Throw my chipper out. Okay. All right. So this program is a mathematical program. Okay, so it's Mathematica. So it's not a PowerPoint. So I have to kind of scroll through some things and describe what I'm doing. So hopefully I can make it quite clear of what I'm doing. Okay. So I call it dodecahedral Rubik's shape because I don't know what else to call it right now, because it is dodecahedron. Okay. I can't really say Rubik's cube because it's not a cube, right? But it is a Rubik's style shape, right? Because basically each side rotates. That's what Rubik had designed. Okay? So again, golden ratio. I'll just, again, quickly describe a few things here. As we said, a transcendental number. There's an approximation of it. And I mentioned before, Fibonacci numbers. These numbers show up in nature all the time. A lot. And if you remember, you start off with the first one, 1, 1. So Fibonacci of 1 is 1. Fibonacci of 2 is 2. And by the way, Fibonacci, that name comes from Leonardo da Fibonacci, okay, who is Italian, I believe from Venice, if I'm not mistaken. He went to North Africa and found the Hindu Arabic numbers, the numbers we know today. And he wrote a book in mathematics back in early, well, before the Renaissance, back in the 12th century, I believe. And he wrote about these numbers, our numbers, the Hindu Arabic numbers, and described this series. Did he come up with this series? I highly doubt it. But it is still attributed to him because it's in his book. But anyways, if fib of 1 is 1, fib of 2 is 2, and then how do you get the third one? Well, the third one is simply, if you look at here, fib of 3 is fib of 2 plus fib of 1. So it's the sum of the previous two numbers. And you can see, 3, well, what is 3? 2 plus 1. What's 5? 3 plus 2. What's 8? 5 plus 3. What's 13? 8 plus 5. Okay, so on and so forth. Now, my purpose is not to talk about the Fibonacci numbers, but you can see, or at least can't really show you here, but if n gets really, really large, the nth Fibonacci over the n minus 1 Fibonacci is the golden ratio. So when you're actually solving a closed form formula for the Fibonacci, you actually incorporate phi, or the golden ratio. And I didn't have time to go over through this in the PowerPoint, but just some quick fundamental properties. As I mentioned earlier, 1 over phi is phi minus 1. Some interesting properties. And if you do the sum of all the fractions, the powers of the fractions, for example, 1 over phi, 1 over phi squared, 1 over phi cubed, to infinity, you get phi. That's one of the reasons why it's called the golden ratio. Because the sum of all those fractions actually equals itself, the phi. So it's the only one that does that. Okay? Okay, so I'll just skip the rest because it's not really the most important. Okay, so now, focusing on that shape, which is moving around with you guys, I had to start. So remember, what am I trying to do here? I'm trying to build this shape, right? So I have to basically discover all the mathematics about that shape. I have to find out what it's all about. So the first thing I need to find is some special triangles, because I know each corner of that vertex is 108 degrees of a pentagon. Okay, so what I found was that you can use a special triangle. So we know in trigonometry there's 2 special triangles that you're most familiar with, right? The 1 square root of 2. Yeah. Okay, that's easy one because they're both 45 degrees. The other one is 1, 2 square root of 3, right? It's 30, 60, 30, 60, 90 triangle, okay? So those are the special triangles we're most familiar with. But here's a couple special triangles, 54 degrees and 36 degrees. And what's interesting is, remember the cosine of pi over 5? Ah, there we go, right? So it's cosine of 36, it's pi over 5, right? It's phi over 2, right? So interesting, right? So that's the relationship. So 2 cosine of 36 is phi, okay? So here's the special triangle. We got phi here, and we got the square root of 3 minus phi. And I'm going to come back to that number, because you're going to see it's the length of one of those edges. And I will take that shape back in a minute here to show you, okay? So this is one special triangle. Other special triangle, which we will use later, is 1 over phi. And remember, what's 1 over phi? Phi minus 1, right? Yeah. And it's 72, 18 degrees. You got 2 over here, and you got the square root of 2 plus phi. So really interesting special triangles that incorporate the golden ratio. Okay, so I'm just going to grab that shape back. All right, take the shape back. Take the prop out of you. Okay. So, the Pentagon. No, we're not in Washington, D.C. Oops, sorry about that. Uh-oh, what happened? Sorry for that. 1 sec. I erased it by accident. Okay. The Pentagon. Okay. We're not in Washington, D.C. Okay. So, if we're going to start with anything, we've got to start with the Pentagon, right? Because these are made up of 12 pentagons. Okay. And these are regular shaped. I don't show you any of the math behind here. Okay. I've got other mathematical program that shows how I did all this, okay? This is just a presentation from Mathematica. But anyway, I had to draw out the pentagon, okay? So that's why I call it the Pentagon. Kind of funny, right? And what's interesting about the Pentagon, here we go. Now we're going to start with golden ratio. Let's scroll here. Notice that if you take the Pentagon, and you have what we call circumscribed radius, right? The circumscribed radius means that the pentagon fits on a unit circle. So this is 1, right? So I'm going to do it as a 1. Now, is this 1? No, right? But it's just, you can consider it a unit. So that these ratios are phi over 2 to 1 or 1 over phi over 2. Depends on how you look at it, okay? So it's interesting that this is what we call the inscribed radius, okay? And this is a circumscribed radius, okay? So already within the pentagon, you start seeing golden ratio pop up. Because remember, I need to know all these angles and play with them in order to build this thing, okay? I mean, not this thing, but the shape that I actually had to turn, right? So this is basically just going through all the math of how I did it. I'm going to try to make it as simple as possible, but I promise you I have a lot of graphics, okay? I'll try to play with it as much as I can. So here we go. So now, if I go down, right? Well, I know, because this is 108 degrees, if I draw from the circumscribed radius to the inscribed radius, I know this is phi over 2, this is 1. Well, there's my special triangle again. We just talked about that, right? So therefore, it's a half of that, because that's normally 2 and this is phi. So this must be square root of 3 minus phi over 2. So you know that this length, okay, is going to be square root of 3 minus phi times this length from here to here, okay, if that makes sense. So this is important math. So I'm just kind of going through the math with you. I hope I don't bore you here. I just want to show you how I did it, okay? And so I need the length per side. This is 3, square root of 3 minus phi, okay? So with 12 regular polygons together, we get a dodecahedron, and you guys have already seen that, but I'm just going to scroll it. See, this is done with Mathematica. See how it turns? Is that cool? I like it, right? You can rotate it around. It's kind of shiny. Ooh, nice and shiny. Mathematica is a great program I've had used for a long time. So that's the dodecahedron, okay? And even though you know about the pentagons, it's not entirely obvious how they fit together. This is easy because I can just take 12 pieces and put them together, and they automatically go together, right? But if you're going to make a shape where things are moving, I need to know a lot more information, right? So putting something like this together is it's pretty straightforward, actually. Because I just take these shapes and put them together. Okay, I don't have to bevel any of the edges. Okay. So let's move down here. That's what I did here. Okay, so I won't go through a lot of this too deeply because it's a lot of math, but what I want to find is what we call a dihedral angle. So this is some good lessons for geometry, three-dimensional geometry. The dihedral angle is that angle right there. It's the angle between two planes. Okay, so you see where my fingers are? Okay, that angle right there is what we call the dihedral angle. So I need to know that. To make this, I didn't need to know that. They just come together and they automatically join well. But again, if you're going to make something that's, bulky inside, you need to know, how they join, right? So you need to know that angle. Okay? So this is what I'm going to do next. I'm going to find these angles. So, and you can see, I'm going to, this dashed line, I'm going to chop this out. Okay, so this line, you can imagine here, I'm going to take a cut here, and a cut here. I'm going to cut it here, right? This way. Okay, so I'm going to take this piece out. Because I want to find that angle, right? I want to find this angle. That's what I want to find. Okay? So you can see with these pentagons, oops, wrong mouse. I can scroll around, right? I can flip it upside down. That's the inside, right? Okay? So you can see it, how it's three-dimensional. Okay? Alright. So that's it there. So I'm taking that slice, and what I'm going to do is I'm going to move it down here, show you. So now I've got this here. So this is going to be at 90 degrees, okay? And I got this line, it's kind of hard to see here, like this. That's better, right? I want to be able to find this angle right here. Okay? So I have to find triangles to build this, okay? So, okay, if I can show you here, I'm going to recreate this triangle right here. You guys see it? And this dashed line here, okay? So if you look down here, it's right there. Okay, so that's that dash, that's that line there. That goes to the end of the triangle, up to here, and that is the dashed line. So I guess in a sense, it's the best way to show you that on here. I guess here, right, I'm going to draw down here. Okay? And I'm going to draw a line up here so it hits 90 degrees here. Okay? So I won't go through all the math because you can see it on your own time. It's a lot of, what I'm trying to show you, trying to impress upon you here, it's nothing, there's no calculus involved, it's just trigonometry. It's maybe not even high school geometry, maybe middle school, I don't know, whatever middle school geometry was like here. But it's just really just using the Pythagorean theorem over and over again. Okay? So, again, there's my special triangle, right? I need to find L, okay, so I'm just going to quickly run through it here. So I do some math, okay, because there's lots of there's what we call similar triangles. Everyone here has done similar triangles in geometry, right? Okay. And this is my dashed line. I would need to find that M. So I want to find that triangle. Okay, so I can find that angle, right? And I find that this length, again, includes phi. 1/2 phi, square root of 3 minus phi. Okay, it keeps coming back. Doesn't leave us, okay? So it's full of golden ratios. So could I find this M? Well, yeah, I mean, trigonometry, no problem, right? It's a wonderful thing about trigonometry, right? Wonderful thing about tigers, right? Like that. Reminds me of that little blurb you used to hear on the commercials all the time. So using triangles, or trigonometry, pardon me, we get 1/4 phi, just 3 minus phi. So now I've got that length. Okay? I'll skip through this a little bit faster. There's just a lot of math. But you can see, I just want to impress upon you that it is basic geometry just done in a special way. Okay? And the knowledge of how to manipulate phi. How do I get all these numbers, these phi? Well, if you go back to my first part of this thing, I showed you all the special relationships, right? Phi squared, for example, is phi plus 1, okay? So on and so forth. 1/phi is phi minus 1. Has some great properties, so it's easy to use. Okay? I'm just noticing 60 degrees. I was able to use basic properties of 60 degrees. 60 degrees, obviously, when you have that, it's called equilateral triangle, and it's also a regular shape. Okay? And I'm able to get properties here, because I know that this is phi square root of 3 minus phi. That's half here and another half here, right? Okay? So now, let's take this information, and we're going to go back, and we want to find that angle right there. Okay? The dihedral angle. So I just split it in half, guys. I know this length, right? I know that length. And easily, using some basic trigonometry, I'm able to find the dihedral angle, and it's 116.565 degrees. So that's going to help me a lot. Because remember, if I want to make this thing turn, right, I need to know how those guys meet together. That's how, and I'll show you what the pieces are in a minute, okay? I'm going to break it apart now, okay? So I need to know those angles. How do they meet? It's very critical, right? Okay, so my ultimate goal was to make a dodecahedron toy similar to a Rubik's Cube. As I said, each side would rotate around adjacent 5 sides. So you can imagine, right? It's complicated, right? Because if I do this one, what's adjacent mean? Well, adjacent to this triangle is next. This is adjacent, this is adjacent, this is one adjacent, this is adjacent, this is adjacent. So you imagine when you turn, right, all that stuff's going to change. Okay? So that's what it is. And when, if I turn it right, this comes over here. If I turn this one, now this one goes down here, right? If I turn this one, this now goes over here. It can move around. You can literally migrate this thing through the whole piece. Okay? So I have to know several things that I'm going to build, right? I need to know I've got to build on a circular track, which I'll show you, inside the superstructure, and it needs to switch the tops. Okay? What's interesting is when you turn these guys, what's really changing? This piece here, which I'll show you later, will never change, right? Actually, just the outside pieces change. Okay, these will change, but the inside will never change. They just sort of rotate, spin around this way. Okay? Hopefully I can show you that. Okay, there's the dodecahedron again, I'll skip that. Okay, so what I got this. Now, what I want to do, what I'm going to plot next, is I've got to figure out a way so I can allow this thing to turn, right? I want the top to turn, yes? I want this side to turn. So I need to split it into 3 pieces. So you just do the design, right? I'll show you a line printout in a minute. But I mean, thinking ahead, right? I need to know I want to split this into thirds, each side. So I can have a piece here. So I can have a piece here and down like this, right? And a piece here and then a piece over here. So I want to be able to spin it, okay? So what I did here next, this is in the outline form. I don't know if this is really helpful or not for this presentation, but you can kind of see it if I rotate it. Watch when I rotate it. Can you see the pentagon? I mean the dodecahedron? Can you see it? Where those dots are where I'm going to connect the lines in a minute here, okay? It's kind of cool, right? You can see it spatially, right? It's moving around. Okay? So, and here's the dash, right? Here it is in pentagon form. So it's hard to see, perhaps. I'm going to sort of rotate a little bit here. Okay, so it's a bit confusing, but if you've got, watch my laser, pentagon here, 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 and here, right? These are actually all pentagons. Another one here. Okay, I think I'm losing myself here, up here, right? It's just like, confusing, and then it's like, well, I'll fall over, right? Okay, so, but I'm doing that just to show an outline of what it's going to look like, right? So, I'm going to take this here and map it on to this. Okay? That's my purpose. So watch what happens. There it is. Okay? So this is a superstructure. And if I rotate it, you can see this is what it's going to look like, right? Okay, so that here is mapped onto the dodecahedron. And that's what it looks like. Okay, they fit nicely, right? And you can see, right, if I'll turn it maybe here, you can see that I've got a, it's hard to see from here, isn't it? The light green doesn't really help that much. But anyway, there's a piece here, you see that? There's a piece here, and it's the same piece, right? These are the same type of pieces. So you got 1, 2, 3 type pieces. So it's hard, yeah, it's kind of hard to see. I apologize for that. Maybe that's easier. Yeah, maybe right there. You can see it better. So you can see it's mapped here, right? So this is one piece here. One. Okay? And then here's another one here. Okay, it goes up the same way. It's inside. I'll show you the individual pieces a little bit in a few minutes, okay? And then I've got this corner here. And then this is one piece, that's one piece, and that's one piece. So it's made up of 3 different pieces. Okay? Alright, so this is what it looks like with them all together. This is probably a little easier. It's not fully formed yet, but this is what it's going to look like without the tracks. I haven't done the tracks yet, or how the things are going to move around. Okay, so this is what it looks like. Maybe you can see it a little better. Can you guys see it better? Right? You can see the inside, right? It's pretty cool. Mathematically, it's a really good program. So you can see now, I think pretty clearly, you can see. Here's one piece, right? Here's a second piece, or over here. See, these are the same, right? Same, and same, right? And these corner pieces are the same. So what is actually going to rotate? What's actually going to migrate around this shape? Well, if you think, you imagine, right, this thing's turning, right? I'm sorry, I have no animations of it turning. That'd be a little bit, that's a scale upwards, which I don't know how to do in Mathematica. But you can imagine if this is turning, right, that is going to move over here. And if I turn this one next, right, this will eventually move over here, right? But notice that this and this will never turn. They never move. Okay? So, I think it's pretty cool. Like, you see inside, right? It's kind of wow. I like it. It's like mesmerizing. Ooh. Well, how long would we do that? Satisfying, right? Okay. So you can see it, right? Okay. Okay, so let's move up. So I have that, and I'll show you the individual pieces in a minute after I show you the tracks, and then we'll hurry up here and finish up. Okay, so, okay, let me just go back up here. Notice on this is the face here. So what am I showing you here? I'm showing you this part here, right? But I'm gonna move it down a third, right? So I want to turn this thing. So I need another triangle or pentagon down a bit, right? Okay? So this is it right here. Okay, so that piece is stuck in there. So I have to, because I have to make these pieces, right? It's going to be slanted off. Okay, that dihedral angle, 116.56 degrees, okay, or 5.7 really. Okay? So what do I need to do now? Well, I want this thing to spin around itself, right? Now, if it had a manufacturing, what we would probably do is be a little bit different than this model. We'd probably put an inside dodecahedron, and it would rotate around that to be easier. But I didn't have that. So all I'm doing is rotating the pieces on themselves. I don't know if that makes any sense, but I'll try to explain that. But I'm going to put tracks here, because this thing's going to turn, right? This is going to turn like this, or like this, right? So these guys have to go around some sort of track, right? They have to stay together, right? So if this one moves around here, it's got to stay together, but this one can move down here. It's got to now fit onto that track and move down, right? So that's what Rubik's was challenged with. Can you make this thing stable and move these pieces around different tracks? Does that make sense, guys? I don't know if that's making sense or not, but maybe I can move it up a little bit. See, if I move this around, say if I move this, I turn it this way, right? That's going to come down on here, right? So it's going to be on this track. Yes, this track here. Well, now maybe I want to move this way. Well, this one's over here. Now it's going to move down this way, right? It's going to fit into the next track. So in other words, the tracks have to intersect. Okay? So I have to draw a track. So here I'm going to do that. I'll bring this back. So here's the triangle, the two triangles, and there's a track below. Okay? Those are the two triangles, and they're going to be joined up here in a minute. Okay? So I have to draw the track. So this thing's going to turn on that track. Okay? And I said about 72 to 77% of circumscribed radius of each inside pentagon, but I just sort of guessed. I just did what I thought was best. There's no reason why. It must be between 72 and 77%, but it seemed to work the best. I don't know. Okay? And then if you graph them all, I don't know if you guys can see it. It's like a ball, right? So what I want to show you, maybe, here, let me just move down one first. Just look at three tracks, right? Notice that over here, see how they intersect? See how tracks intersect here? Tracks intersect here? And then they intersect, if I move it up here, getting confused. See how they intersect over here? See here? Here and here? They all have to intersect to make it work right. Because think about it, right? You've got to spin it around, right? This thing spins around and stops here. It's going to move over here now. Or if it's over here, now it's going to move this way around. They have to intersect. That's why if you have a Rubik's Cube, if you try to turn it halfway, you can't turn it out. It's got to be fully turned, right? Because you're fitting into another track, and then that moves this way, right? So when you do them all together, like this, I mean, you get this nice little, that's what it's going to look like globally. Okay, so it's complicated, okay, but it's not. I mean, it's a special formula. They're all sat